Okay, so where are we? We're starting chapter 7 today, which is external flows. And we've talked a little bit about some of the topics looking particularly at turbulent boundary layers. And that has been sort of the background information we've been using for chapter 6. We looked at a solution of the turbulent boundary layer. We went to the Moody diagram, and then we went to Holland and Swami Jain. This chapter is going to more specifically look at those boundary layers and talk a little bit more, because those boundary layers have no limits to how far they can extend. So it's external flows because the body is completely immersed in the stream. Viscous effects are generally confined to a thin region near the body's surface, the boundary layer, and its wake. Flow is nearly inviscid away from the body. And one of the things that we don't talk about in this course, and you may want to sort of look out for your own interest, is potential flow, where you start to do stuff with that inviscid region. Flow, okay, unlike internal flows, boundaries are unconfined and can grow. And so that means that any type of internal flow, you have boundary layers that grow off of the walls, and then they sort of meet in the middle, but they can't grow more than that. Where this is important is aerodynamics, of course, hydrodynamics, transport, and wind engineering. And again, I'm going to put a sort of shout out to RWDI if you want to find out more about bridge engineering, solar engineering that they do. External flow is highly dependent on the Reynolds number. And Reynolds number in this case is going to be dependent on length. And so length is going to be defined along whatever you're looking at. So here, for example, are two cases with a thin plate. And you can see that the effect at the walls in both cases, in a laminar case over here, where you have zero velocity and you have a free stream, and a turbulent boundary layer, well, maybe I'll just sort of zoom that. There we go. Turbulent boundary layer, where again you have zero at the wall, and then very close to the wall, so very thin layer, you approach the limit of the outer boundary layer. So you can see that that's one of the big differences, and it's one of the reasons why you would want to have turbulence, because it's a lot easier on drag and body force. Since, again, I am a shameless self-promoter, as you go into MC 102 and you see that large research poster with all of the activities done in MIE, you'll notice sort of in the bottom a really nice flow visualization. That's me. Thank you. And that was done by a PhD student of mine, Mark Firo, about 5-10 years ago. And it's looking at flow past an airfoil. So we have an airfoil over here, NACA 0025. And NACA is just for National Aerodynamics Committee. I forget what it's National Aeronautics. It was done in the 1920s, and it's the precursor to NASA. And what you're looking at is a controlled flow. So we provide small devices on the wing, and those small devices act to add momentum very close to it and bring down the size of the wake. Otherwise, we'd have a separated flow, and the flow would look like this. All right. We've talked about the Blasius solution also. And the Blasius solution is an exact solution, and it gives you the boundary layer thickness and it's, again, equation numbers I hope are correct. Sorry, for laminar flow, I just want to make that fit. For a laminar flow, it's delta over x is 5 over Reynolds number based on downstream distance. And we base everything on downstream distance which is x, so as you move downstream. Wall shear stress is given as 0.664 over Reynolds number x. So this all goes back to chapter 5 when you did the non-dimensionalization and started to look at different types of values. And you can see, for example, boundary layer thickness that is defined with respect to some y parameter, which is the boundary layer thickness, and it stops really at about 5. We can't measure 100% velocity, so we won't get little u over u, which is little u is the velocity in the boundary layer, big U is the velocity in the free stream. We're not going to measure 100%. So we come close, and we assume that once we hit 99%, so roughly 4.85 on that scale, we are at the edge. Turbulent flows tend to be more difficult, and because they're more difficult, we have sort of done an approximation, and we have something called the 1/7 law. And u over u in that case is a function of y over delta, the boundary layer thickness. Again, delta is the thickness that we've assumed. It's about 99%. of the free stream velocity, because that's a limit of what we practically can measure. And we get something that looks as 1/7. And if you remember the slide I showed you right at the beginning of the lecture, you saw the difference in terms of the shapes of the turbulent boundary layer versus the laminar boundary layer. The turbulent boundary layer reaches its maximum velocity very, very quickly. On the other hand, the laminar boundary layer takes a long, thick region before it actually gets there. So we have a set of practical formulas, and these are approximations, excuse me. And these approximations are that delta over x goes as 0.16 Reynolds number to the 1/7, and coefficient of friction is wall shear stress over a kinetic term, and basically 0.027 over Reynolds number to the 1/7. Turbulent boundary layers tend to grow much faster. And all that means is they grow much faster because they reach that 99% velocity ratio much earlier than laminar ones. So laminar one goes as x to the 1/2, downstream distance is x again, and a turbulent boundary layer goes as x to the 6/7. So if we have water, we have nu, which is 1.004 times 10 to the minus 6 meters squared per second. We assume laminar flow. And maybe I should read the question. Long, thin, flat plate is parallel to a 6.1 meter per second stream of water at 20 degrees C. At what distance, x, from the leading edge will the boundary layer thickness be 2.54 centimeters? We start out by assuming laminar flow and look at what we get. So if we do that, at 0.0254 over x is equal to 5 over ux over nu, square rooted, we get 5 over 6.1 meters per second, 1.004 times 10 to the minus 6, all to the 1/2. And we get x is equal to 129.5. So we check that with Reynolds number, and Reynolds number is Ux over nu, 6.1 over 129.5, and 1.004 times 10 to the minus 6, which is 7.8 times 10 to the 8th. So this is a very high Reynolds number. And one of the things that you will notice in this chapter is that we don't achieve a constant value. So for example, when you're dealing with pipe flow, you just did UD over nu. And so you would have the same Reynolds number throughout the pipe. And that's because you have fully developed flow. It's a reasonable assumption. Transition is 5 times 10 to the 5th. And again, one of the things that you have to get used to is that with pipe flows, we said 2300, 2100, whatever it is. But here you're at 50,000. So again, that's a difference that you're going to see when you deal with pipe flows or internal flows versus external flows. The trigger to go from laminar flow to turbulent flow is going to be different in both of those cases. So if we do that, and assume that what we have here is a turbulent flow, which is reasonable, then we have to calculate everything again. So we have Ux, X, nu, and we end up with x to the 6/7 equals 3.29 meters. And one of the things that you'll notice here is that this is a lot faster. So we needed to go 130 meters in a laminar case, and we needed to go only 3.3 meters in a turbulent case. Reynolds number in this case is going to be 6.1. Oh, wait, x over 6/7, so x is equal to 3.8 meters. X is equal to 6.1, 3.8, 1.004 times 10 to the minus 6, 2.3 times 10 to the 7th. And it's clearly turbulent. Again, you're well past this 50,000, and now that you're well past 50,000, your numbers kind of make more sense. Any questions on this one? Go ahead.
So we first make the assumption that it's a laminar flow, and when we see that the Reynolds number is greater than 50,000, we then make the assumption it's turbulent flow, and then make it certain.
Yeah. That's the more sensible way. With this one, I might have guessed right away it was turbulent, and I would be okay, but it would be good to go back and check. Sorry.
What if we assume it's turbulent, but it's not?
Then you're going to be wrong if you don't check. So it's better. The tendency, especially with something like this problem, you look at this and you say 6.1 with water, 20 degrees C. That's a very high velocity. And 6.1 in water, going past the flat plate is going to trip very quickly or transition into turbulence. And so experientially, I would go right away with turbulence. I would not recommend that you do that right now. Eventually, you'll do that. Okay. And what you're going to find in this particular lecture, especially this section of it, it's really just let's use these empirical relationships and see how far we can go with them. And that's about it. So this is air. And we can calculate the Reynolds number at the very end. Okay, sorry, maybe I should read the question. Compute the trailing edge boundary layer thickness for a flow at 0.305 meters per second past the flat plate. The length of the plate is 0.305 meters, and calculate it for both air and water. And if you do that, and it's kind of annoying because both numbers are the same. So in this case, the Reynolds number ends up being 6,100, 6,200. And this is less than 50,000. So laminar. And so delta over L, you have the exact solution, is going to be 56165 square rooted 0.0637. So delta is going to be 0.0637, 0.305, 0.0194 meters, or about 2 centimeters in height. So you're just using the basic relationships. You know that it's laminar. You've calculated that it's laminar, so you know the relationship that you can use. Things get a little bit weird because with water, we go from 1.5 times 10 to the minus 5 to 1 times 10 to the minus 6. So we're going to increase this by an order of magnitude, which you've probably already guessed is going to end up causing this to be turbulent. Or not. Hey. Okay, and this is turbulent, and I have the wrong answer here, and I'm going to have to fix it because its Reynolds number is equal to UL over nu, 0.305 meters, 0.305 meters per second, all over 1 times 10 to the minus 5. And in this case, Reynolds number is 92,600, which is, oh wait, it is laminar. Sorry, it's not 50,000, it's 500,000. Hold on. I can't do 10 to the 5th in my head. All right, so there you go. So it's laminar in both cases because it's less than 500,000. And let me just go back over these notes to make sure I didn't. Maybe I was clever. Okay. Yeah. All right, so it is less than 500,000. Sorry, that's the number you're looking for. So 5 times 10 to the 5th. Delta over L is 0.0164, 0.305, or half a centimeter. So higher momentum in the boundary layer, higher momentum outside, and that affects everything that you're seeing. Yeah, it's 5 times 10 to the 5th. Again, you're going to use a lot of charts. And you can see that this chart has a behavior that is awful similar to what you saw in the Moody diagram. You have a smooth section over here, which is equation 727. You have a transition zone, which we generally ignore. Again, with turbulence and laminar flow, in this course, this is a mystery, and you kind of ignore it. But over here, you have C sub d versus Reynolds number, and you have it as a function of roughness. Ugh, there we go. But unlike pipe flow, you don't do epsilon over d, you do L over epsilon. You also note that after you reach a certain point, and it's because of this you have slightly different sort of shapes to these curves, it reaches a flat zone. And that flat zone extends all the way across as you increase Reynolds number. So it doesn't matter what you do. If you do the model here or here, you get the same C sub d. And so you can, that's how you kind of do the matching with experimental data. Yeah.
So where are the blue ISO lines like indicating here?
So this dash line or the other lines? Sorry, these lines right here? Yeah. Those lines are different roughnesses. So again, L over epsilon, not epsilon over L. And you'll notice that that dash line indicates the point where you go from a sort of not quite fully rough to fully rough. And when you have fully rough, you have a linear region that extends outward. Go ahead.
I just wanted to ask, so if you don't have any external flow, your Reynolds number for your turbulent flow would be more than 4,000. But if there is an external...
So maybe I should define that first so we kind of agree on things. So with any type of external flow, I will put an object in a flow. And in that, so if this is a wind tunnel, for example, this is my external flow. It will approach this flat plate, and initially it's only here at the very beginning where you see an effect from the wall. So the viscous effect, and everything away from it sort of doesn't affect anything. It's not affected, the free stream is not affected. But as you move downstream, the effect of the wall increases. Now, this is not laminar or turbulent. This is just some case. So you'll see, yeah, well, I can actually show that. Right here. Ugh. All right. You see this black region that is before the trailing edge of this wing? That black region is the viscous layer. So that's where viscosity is playing a role. Everything outside of that is the external flow. So the internal flow is affected right near the wall. Okay? So if, in all of these cases, you can't have a zero flow, because if you had a zero flow, there'd be no flow, and Reynolds number would be 0. All right, another one. Sharp flat plate, length of 50 centimeters, B of 3 centimeters is parallel. So its length is 50 centimeters. Its width is 3 meters, is parallel to a 2.5 meter per second stream. Find the drag on one side for air and water. And again, you'll notice there are a lot of differences as you go from one to the other. So for water, or air, excuse me, So this is where you have to get used to the idea of defining Reynolds number in a way that makes physical sense. So you have a sharp flat plate, and at the very top I've drawn a very bad drawing of what that plate looks like. Flow is coming from top to bottom, and across the flow, 3 meters, is the length of that airflow or that plate. The distance that the flow travels across the plate is ½ a meter, which means that when I'm calculating my Reynolds number based on length, I'm not using 3 meters. I'm using 0.5 meters. So for laminar, oh wait, this is 83,300, and so it's laminar right here. So that's just the top view. C sub d is 1.328 over square root of Reynolds number based on L, 1.328, 83, 300 square root, which equals 0.00046. So I can calculate the drag coefficient. I have that relationship from the beginning of the lecture. And from that, I can calculate the magnitude of the drag. And drag is equal to C sub d times 1/2 rho u squared times a cross-sectional area, which is going to be b times L. So that's 3 times 0.5. So it's not a very large number, 0.026 newtons. Okay, for water, and maybe just a quick comment here. So the reason I needed the density is to calculate that total force. Now for water, I'm going to have a very high density and a drop in the viscosity. And here, my goodness, I end up with a turbulent boundary layer. Now, of course, I'm going to write them as 10 to the 6th so I can avoid trying to remember 10 to the 5th, but it's 1 million, 1.2 million, 1.24 million. There we go. One over 1.24. 10 to the 6th. Ah. And C sub d in this case is just going to be 0.031 divided by Reynolds number to the power 1/7. I've calculated that, and I get I'm going to use something called the transition formula. So it ends up being 0.031 over 1 point, oh no, sorry. I made too much. I want it cleaner. 1440 over Reynolds number to the power L, which is equal to 0.031 over 1.24 times 10 to the 6th to the 1/7 minus 1440 over 1.24 times 10 to the 6th drag, or C sub d, is equal to 0.028, and d equals C sub d 1/2 rho u squared times b times L. So this is just, whoa, 1, 2, 3.
Right now?
Yeah.
Why are we using the transition formula, and then where did we get the minus term? Is that just a part of the formula?
It's a part of,
Why are we doing this?
we're just subtracting off the laminar, or basically we're subtracting off the maximum value of the laminar term. It's all turbulent at this point. And so when we calculate it, it doesn't go from 0. It doesn't take care of the 0 part. So this is another empirical formula which I should put into the notes because it's turbulent.
So if it starts from laminar to turbulent, you have to add that term, or?
Yeah, you have to take care of it.
But if it's already turbulent, then you don't have to worry about that?
You have to worry about it because it always will be turbulent, or laminar to turbulent. So one of the things that's going to happen, because you remember your Reynolds number is based on the length of the plate. So you'll have an initial region which is laminar no matter what. It may be very, very small, but it will transition, and when it transitions, you have to consider it all the way through. Okay. Go ahead. 0.03. Oh, this right here? Yeah, that's from the relation, the turbulent relation. So this is, again, empirical. And one of the problems with this chapter is that there's not a lot of derivation here. You're going to be using a lot of empirical relationships, especially for the turbulence. For the laminar one, you have this 5 that comes out of the basic equations of motion. You solve for it, and then you get that right out of it. But this one is more experimentally based.
So you're saying that this is like specific to just
To turbulence. Yeah. 1440. I have to look up the number exactly, so I don't remember offhand, and I will look it up. But it is basically it defines the edge of your boundary, or of your transition. For all flows, basically. So it's going to be in there, but I have to do a better job in terms of showing that. Okay. All right. What's interesting about this is that, yes, it's a very high it's a very high Reynolds number. It's turbulent, and the associated drag with that, when you change it from air to water, goes from 0.026 newtons to 500 times, 2.6 times 10 to the minus 2 to 13. 10 to the 2, so it's about 10,000 actually. All right. Air at 20 degrees C, 1 atmosphere, flows at 20 meters per second over a flat plate. There's a pitot at y equals 2 millimeters, and it reads a height of 16 millimeters. Reads h equal, or a head, excuse me, a head of 16 millimeters. Barium red oil, and so you have a specific gravity of 0.827. You assume a laminar boundary layer and uniform static pressure. Find the downstream location x and check if laminar flow is plausible. So what you've done, and so again, this is this boundary layer. You'll notice over here, where it hits initially, there's a 0 velocity and 0 height. And as it moves downstream, we're going to assume that it goes as a parabola. So in terms of what we'll look at, we have rho of the oil, which is 0.827 times 998, which is approximately 825 kilograms per cubic meter. Delta P is rho of the oil minus rho of air G times H, which is 825 minus 1.2, 9.81 times 0.016, which is 129 pascals. The Blasius solution U over nu x, U over U infinity, which is a function of eta, which is your height. And so from the table, or from tables, eta equals 2.42. X. Okay. So you're just trying to figure out what the height is. You're doing a length term, and that length term is going to be associated with your boundary layer. X is equal to u y squared over nu eta squared, which is 0.908 meters. And this is where it gets a little bit difficult. 1.2 times 10 to the 6, which is kind of borderline plausible if smooth. It's likely, in this case, it's likely to be turbulent, and you can have a, I'll start with you. Oh, sorry, in the back, then you, sorry, then you, then you. Yeah, you. Because you're looking at the difference between a laminar and a turbulent boundary layer. The 1/7 is the turbulent boundary layer. The power 1 is going to be the laminar case. So you're subtracting off that part. I'm sorry? Yes, they are. You? Sorry. I don't know. from tables. My handwriting doesn't get better.
And what is the symbol associated with that?
It's basically a boundary layer thickness, but it's not
Like a
quite.
delta?
It's supposed to, it should be a delta. I'm writing it as eta, but it's eta because I'm trying to do this as u over u infinity is a function. I probably, you know what, would make my life easier. Delta, delta, delta. Yeah. So you're dealing with boundary layer thicknesses, you're just rewriting them. Sorry, questions?
For the eta equation with the gravity term, was that derived somewhere?
Which gravity term? Delta? Where? Yeah, okay. Oh, this term at the top, delta p?
The one right below it, with the delta equals y.
No, oh, yeah, that's from the Blasius solution. And basically, it's coming out of this. Okay. And let's continue. Same setup as before, but U is unknown. Manometer, Merriam-Red-Oil, traverse data. So you start at Y of 0.5 millimeters, and you have a head of 1.2 meters. You have 1, 4.6, 1.5. You go all the way out to a height of 5 millimeters and a head of 29.7. So if you do that traverse, one of the first things you notice is that you have very low velocities near the wall. So it's 0.5, which you expect. And between 4.5 and 5, you have achieved pretty much a constant value. And that constant value of the manometer is going to be 29.7. Ew. So if you have the value at the very edge, you can find out what the maximum velocity in the boundary layer, or at the edge of the boundary layer is. And you have 29.7 meters, or millimeters. Or, sorry. Yeah, it's 29.7 millimeters. And you can calculate from that the change in pressure, use directly the Bernoulli equation, and you get 20 meters per second for a velocity. Now, I can extract directly what the boundary layer thickness is because that's going to be pretty much 20 meters per second. That's achieved in the table by 4.5 millimeters. Ew. And if you do that, then you can calculate at the very lowest point the same thing. So you have h equals 1.2 millimeter at the bottom, and it translates to 4.02 meters per second. If you do that, you can also calculate what the velocity gradient is between the lowest measure point and the wall, and that velocity gradient is going to be 4.02 minus 0 over 0.005, 0.0005 minus 0, and so I'm just writing 4.02 over 0.005, 0.005, and so you have a value of 8,040 inverse seconds, which you can use to calculate the wall shear stress. And the wall shear stress is going to be mu times that. So if you do that, you get a wall shear stress of 0.14 pascals. If x is approximately 0.908 meters, the force on the plate is going to be twice that times the shear stress times x, so 2,014 times 0.908, which equals 0.25 newtons per meter. So a force of 0.2 newtons per span of 1 meter. Go ahead.
For del U, you just used 4.02. Why wasn't it 20 minus 4.02?
Because it's not a linear relationship. So if you look at that surface, it looks like this. Something like that. And so what I did was I went to the locus area, and there you go. And here you have u equals 0, and here you have u equals 4.02. I know the distance up is 0.5 millimeters, and so I can do a gradient there. If I try to do that across there, what I'm going to fit across is going to be 20 meters per second. Ugh. And it's going to be that, which is not a real reflection of what the boundary or what the gradient looks like. And it's not the wall shear stress, because I only care about what's happening